Hi, welcome to another video for General Science. In this video, we're going to be discussing energy, its conversion, and conservation. So this video can be used in a chemistry class, a biology class, when you're talking about energy or the law of thermodynamics. Okay, one of the first laws of thermodynamics, or as it relates to energy, is that you cannot create nor destroy energy. Okay, there's also a law of conservation of mass, which you cannot create nor destroy mass. Um, and like in chemistry, matter does not get created nor destroyed. Even when you see something like an explosion, you think, oh, something was destroyed or eliminated. It's not destroyed, it's merely transferred. It's changed from one form to another. And likewise, energy does the same thing. Energy is not created nor is it destroyed. It can be changed, though, to one form, from one form to another. Okay, it is conserved. All right, now let's go ahead and talk about what we're going to see in class. This is called a superheated steam demo. And in this demonstration that I'm going to show you in class, I'm going to show you the various ways in which energy can be transformed. Okay, and what I have here is an image of the general setup that you're going to see. With the exception of the liquid, it's not going to be a blue liquid, it's just going to be clear, normal everyday water. Okay, and then you're going to see, and then there's going to be a large copper wire that's coiled, that's going to stick out of the Erlenmeyer flask. All right, so let me discuss what you're going to see. So the first thing is I'm going to have a plug, and I'm going to plug in our hot pad, our heating pad, into an outlet. Okay. Now that's where our initial source of energy is going to come from. Okay. Now of course that electrical energy comes from a power plant, which comes from other sources like it can come from a geothermal plant, a hydroelectric plant, wind energy, you name it. But for us, it's going to start with the electrical. So the energy that we're going to use starts off from the outlet as electrical energy, which is then transferred into our hot plate, which then is transferred from electrical to then thermal. Okay, you might see the hot plate turn red, or you might just feel the heat coming off that hot plate. Okay, it's going to radiate off of that hot plate. Now here's an interesting thing too, right off the bat, in terms of conservation of energy. Not all the electrical energy that we use or that we gain from the outlet is going to be used to heat up our water, because some of that heat actually escapes, because we're gonna be in an open system, in an open classroom where it's open air, and a lot of that energy can escape, and it doesn't all get absorbed by the water molecules. Okay, so we go from electrical energy to thermal energy. Okay, and then that thermal energy, our hot plate, the heat from the hot plate will then, that energy will then be transferred into the water in the Erlenmeyer flask. Okay, so again, we've transferred from thermal to our hot plate to our water. So let's zoom into our water and see what exactly happens. So what happens is our water molecules, okay, our water molecules, the trillions and trillions of water molecules that make up the water that's in that flask, they are all bonded by something called hydrogen bonds, or it's a force that keeps them together, right? So these hydrogen bonds keep water molecules together. Now what happens is, as that energy gets absorbed by those bonds, and those bonds, they become less stable and they break, releasing each water molecule, each H2O molecule to itself. And that's basically the boiling effect that we see. So when you're actually observing boiling, you're observing water molecules floating, if you can even see them, water molecules floating that have been separated from the larger mass of water in your container. Okay, so that's the boiling effect that you see. So the boiling effect happens when enough energy has been absorbed by these water molecules, by these hydrogen bonds, to actually release the water, and it goes from a liquid state to a gaseous state. So energy is then transferred to the water molecules themselves. Now they will begin to condense as they cool off. Some of these will cool off, and you'll see a condensation begin to develop at the lip of the flask, and some of that condensation will actually make its way through the copper wire, and it will collect in the copper coil. And that's the reason why the copper is coiled, so that those molecules can actually collect in that coil. Now they still have energy in them, even though they're condensing. So what we do, we immediately add additional heat with our propane um, flame. It escapes me right now. Our propane flamethrower. Okay. So in any case, for lack of a better term, it escapes me right now. But we add additional heat. Okay. So we add additional heat, and what ends up happening is that it goes from being a gaseous state to now we're turning it into basically a super steam. Okay. So now you have water molecules in here. Let me go back. You can see the steam kind of come out, right? So that steam, you're not going to really be able to see it. So what we'll do is we'll put a black background to it so you can actually see the steam shooting out. That is super hot. Now think about it. It makes logical sense. If I were to ask you the question, which has the most energy, either steam or water, or even steam and boiling water, it would be steam. So you can burn yourself much quicker with steam than you can with boiling water. So boiling water is not as dangerous as steam, as dangerous as boiling water is. And the logical reason, the scientific reason for that is because steam has a lot more energy absorbed in its molecules than does boiling water. Okay, so that energy we will then transfer. Okay, we will then transfer that energy over to a paper that I will put in front of that steam, and you'll see it. What's going to happen to that paper is that it will scorch as evidence of energy being absorbed by that paper. So we go from transferring energy to the water molecules to then the paper. And you're going to notice that that paper does not actually open up in flames. The reason for that is that because there's so much pressure, because the wind is actually blowing so strongly against that paper, it doesn't allow for a flame to develop. But you do notice that it becomes scorched. So that, again, that's evidence of energy being transferred from the steam to the paper itself. And the paper can't really handle that much energy, so it basically just burns up. So those molecules, the carbon molecules, the cellulose molecules that hold paper together do burn up, and you'll see that when we perform this. So in summary, transfer of energy, conservation of energy. You go from an electrical outlet to our hot plate to then our Erlenmeyer flask. You have to excuse that blinking outlet there. To then our water molecule, right? So the water molecule, our hydrogen bonds will absorb that energy. And then as they condense in the copper coil, we add more heat to it. And then as we add more heat, we develop the steam, that super steam. And then we transfer that energy from the steam into our paper, which we scorch. Okay, so again, energy is being transferred. It's changed from one form to another. It is not destroyed, nor is it created. It is merely transferred from one form to another. Now again, 100% of the energy that comes from the electrical cord does not actually get transferred to the paper. In the process of each of the energy transferring from one form to another, in that process we actually lose some of that energy. So 100% conservation does not happen. Some of it escapes through the air or through even the heating of the, as the coil is heated up, some of that heat is transferred to the coil itself, or it's transferred over to the glass that holds the fluid. So it's not 100% transfer. Okay, so that does it for energy conservation and conversion. And I hope you enjoy the demo in class, and good luck in your studying.